Good afternoon to all of you, or evening or morning, depending on where you are on the planet. And thank you very much for registering and also attending this live webinar from Dr. Emma Schymanski. So my name is Justin van der Hoofd. I'm working at Glasgow Polyomics at the University of Glasgow in the United Kingdom, and I'll be hosting this webinar today, and it's really a pleasure for me to do this because the topic is very much to my heart. So I'm doing this on behalf of the Early Careers Members Network of the Metabolomics Society, and this is actually the 10th in our webinar series, and currently all the webinars are free to attend and also free to look back at the Metabolomics Society website by the courtesy of the Metabolomics Society. And we hope that also this webinar will be available for looking back on the website in the near future at the website, which will be under the tab of resources. So please connect with the Metabolomics Society and also the EMN on Facebook, Twitter, LinkedIn, and there's also the special info.emn email address displayed at the bottom of the slide, where you can send any questions or ideas to, and the EMN will get back to you. So if you have any ideas on webinars or you want to present, you might want to present one, please let us know. So before introducing our speaker, I want to introduce you to the new Metabolomics Forum that we also introduced in Dublin during the Metabolomics 2016 conference. It's a platform where we can talk and discuss any subject related to metabolomics. So Metabolomics Society, hardware, software, databases, etc. If you have any question related to that, you can post it on the forum and you can get answers from other users who are experts in the field. So please visit the forum, create your own profile. Please use your name, because that's pretty good to also know that who we have in the discussions, and use this platform to talk and discuss metabolomics. The link is displayed on the slide, metabolomics-forum.com, and the forum has been used quite actively over the last few weeks. So please join in, and there's a chance that you will get an answer to your question. So, coming to today's webinar, today's expert speaker is Dr. Emma Schymanski, a research scientist at EMN, the Swiss Federal Institute for Aquatic Science and Technology. Her research interests lie in the suspect and non-target screening of environmental contaminants, primarily with LC, high-resolution MS, but also GCMS, and applying structure generation to the identification of unknowns. The contribution of mass spec to open spectral libraries is an essential part of her work, as she's an active member of the Mass Spec Consortium, developing our mass spec in a team of scientists. She also works on optimizing compound database search strategies for candidate selection, and I think on this we will hear more in this webinar, and how to communicate the confidence of high throughput identification results, currently applying this in the Solution EU project for emerging and future contaminants. Together with Seven Neumann, she founded the Casmi contest for small molecule identification in 2012, now into the 4th round. She's an active member of the Metabolite Identification and Computational Mass Spectrometry Task Groups of the Metabolomics Society. So before we start, I just want to point out that there is a question box in your GoToWebinar menu where you can ask any questions during the webinar. So after the webinar, we will select a couple of those questions to ask to Emma, and hopefully get a nice discussion at the end of the webinar. So thank you very much. With that, I hand over to Emma.
Okay, thank you, Justin, for the introduction, and thank you to all of you for attending, and to hopefully some of you in the future who will listen to this at a later stage. Again, before I start, just on my introduction slide, I'd like to point out my website here. I will have a lot of hyperlinks in this seminar or this webinar, and you can actually go to my website and download the PDF where all of these will be active, because the copy you will get on the Metabolomics Society website will be a screenshot and will not have those hyperlinks active for you. So thank you again to Justin for the great introduction. He's already said where I come from, so with that I will go straight into my plan for this webinar today. And because I understand this is is going to be a resource for early career members as well. This will start pretty much with an introduction to mass spectra to make sure we're all on the same page. So to do this, we'll go through a little bit of electron impact mass spectrometry, and I've given it the general term soft ionization tandem mass spectrometry because if I went into the details, this would go way over 40 minutes. What you can see here at the top is basically what we're talking about, a little mass spectrum, and the idea behind the mass spectrum is basically to use this information that comes out of your mass spectrometer to get you to a structure shown at the bottom. Once we've gone through the short introduction, I'll basically go through a brief overview of GCEI-MS libraries, and I've got again the gas chromatography in brackets because not all libraries require this. Then I'll go into MS libraries, again with the LC bracketed. Sometimes these are connected mainly with liquid chromatography, sometimes not. We will get to that. And then right towards the end of this webinar, I'll just have a quick look at some questions. Why do we need so many different libraries at this stage? Are you really sure about your identification, what to look out for, and what to do if your spectrum isn't in the library? I will not go into this in detail, more use these questions to lead into what will hopefully be a future webinar on some of the in silico methods for mass spectral identification where this substance is not in a library. As Justin mentioned, there will also be time for you to ask questions during the webinar. I will actually not see these until Justin reads them out, and we'll have time at the end to go through some of those. So just to give you a brief introduction to mass spectra and how mass spectra are actually created, what you can see here at the left is we have a molecule represented by the grey dot. In a mass spectrometer, this is ionized, and we'll create what's called the molecular ion. This ion can have fragments happening as well, and these fragments will be of different size. Anything that does not have a charge is actually removed in a vacuum, and what you see is only charged fragments in the mass spectrometer. These are then basically bent in a magnetic field, and this magnetic field is actually what sorts them out according to their size, and then we have the detector right at the end that will give us the information of these fragments sorted out by their size. And this is how mass spectrometry works. To give you a very similar diagram, just with something that looks a little bit more like a molecule. And here again an example with electron ionization mass spectrometry. So this is actually a gas phase reaction. Your molecular ion, represented with M, is bombarded with an electron field. A little bit counterintuitively, you're actually forming a positive ion with 2 electrons as a result. So in this electron beam, you'll actually at the bottom form what's called the ionized parent molecule. This gives you, in your mass spectrometry, information about the parent, so the mass of your molecule of interest. But you can also get the fragments in what's called a dissociative result, and this is what actually gives you information about the structure behind your parent molecule. You get this information actually according to the fragments, which has the charge, but also the neutral loss. You do not see this directly, but you see what bits of the molecule are lost. To give you a brief schematic of how gas chromatography works, liquid chromatography works on a reasonably similar scheme, just with a liquid carrier rather than gas. Here you'll have your carrier gas taking your sample into the column. This column then separates your sample according to different properties, and you can see this at the top with your total ion chromatogram. You're basically getting your molecules separated out over time. And right at the back end we have a mass spectrometer detecting your results. So for every time in the chromatogram you get a corresponding mass spectrum. What you see at the bottom here is the mass spectrum of this C40H82, so 1 point of the total ion chromatogram. So from the top, from the chromatogram, we can get some retention time information, and from the bottom, the mass spectrum, we will get our molecular information. So just a brief run through electron ionization mass spectrometry. This is one of the most established mass spectrometry techniques. It's been around for about 50, 60 years now. The advantage with EIMS is that it has very reproducible spectra, so both intensity and fragments. These are reproducible across labs across the world, and this is one of the main strengths. You can see also from the spectrum at the bottom of this slide, this is very rich in structural information, and this is where we get this term molecular fingerprint, because you basically get a whole summarized bit of information about your molecule. Another great advantage with EIMS is there are very extensive libraries available, so in terms of identifying quickly with some of these libraries, you can get a lot of progress very quickly. Some of the disadvantages with EIMS is actually the the nice part of the fingerprint is that you get so much information, but the signal is actually spread all over all of the fragments, so this is a lack of sensitivity. There is also quite a limited compound range because you require the coupling with GC MS. So this means that derivatization is often required, and this can add to the complexity of interpretation. Although it's not visible or it's not obvious in this example, there are around 20 to 40% of EIMS spectra actually have the parent ion low or missing, and this makes actually retrieving information about the parent molecule quite difficult, so actually estimating the mass of your molecule. You can see here we actually have quite a nice pattern for the parent ion. So EIMS is a very nice all-in-one spectrum. You have all your information on one page. I'll just show you a little example with diclofenac. What we can see here is what's called the M peak. This is a 295. This gives you the molecular weight or molecular mass and also the isotopic distribution of the elements. So what you can see here is at the M+2, we actually have a very high intensity. This gives you a nice indication that we've got 2 chlorines present in this molecule. What we also have with EIMS is very systematic fragmentation, and this is what gives you the structural information. So you can see here we've had a neutral loss of water. We will actually not see the water ion because it's below our mass range. We can also see the loss of a chlorine here, and you can see already the isotopic pattern has changed, telling us we've only got 1 chlorine left. And you can see also we have a loss of the CO2 as well, so you can see basically our fragments are making the molecule gradually smaller. I briefly mentioned derivatization, just to give you a very quick look at this. Derivatization basically means you're putting a protector group on some of the polar groups to make these molecules more amenable to gas chromatography. What you can see though is that it actually changes the mass spectrum quite dramatically. So whereas our unprotected molecule has 129 as the largest peak, here all of a sudden at the bottom we've got 144, and we're getting some higher masses. We've also got this peak at 73 coming up, and that belongs to the TMS group that's been used as a protector. So the more protecting groups that you actually add to your molecule, the more this actually changes the mass spectrum. So a lot of GC-MS libraries also have spectra of derivatives and underivatized substances. Moving on to what I've given the general title as soft ionization mass spectrometry, because there are actually many different ways to ionize with higher resolution mass spec. I'll just take the example of electrospray, which is one of the most common, otherwise known as EASY. The advantages of soft ionization MS is this actually allows you a much broader coverage of the compounds. So this will give you a coverage of polar and thermolabile substances beyond GC-MS techniques. Because it's a soft ionization technique, the parent mass is often available, and these are now often available at high resolution and very accurate mass. So this helps a lot in identifying the mass of your parent. But we have the disadvantage of getting a lot of adducts and in-source fragments that increase the complexity of the spectral interpretation. Compared with EIMS, there's actually much poorer reproducibility and fewer fragments. This makes the spectra less comparable, and it also gives you less information with the spectrum. We'll get back to this a bit later. You also, with EASY as a source, have quite a bit of ion suppression, which can affect your analysis. So just to give you a picture, this was the GC-MS spectrum I showed before of sulfur methoxazole. And here now is the corresponding LC-MS-MS spectrum of sulfur methoxazole. What you can see straight away is we have quite a bit less information in the spectrum. So this makes LC-MS-MS sometimes a little bit more challenging. What we do have with EASY and with some of the other ionization techniques is the presence of common adducts. And again, I said in the previous slide, this can sometimes hinder the interpretation because it makes it a lot more complex. On the other hand, this can really help you calculate the correct parent mass because you will actually see some or all of these peaks in your spectrum, and you can know through the mass difference that this one must be the ammonium adduct, therefore we are very confident about the parent mass in this case. The presence and the intensity of the adducts actually depends a lot on the substance, but also the conditions that you measure in, and you can actually tailor your conditions to only form one adduct if you really know what you're looking for. In alternative ionizations, for example APCI or atmospheric pressure chemical ionization, you can also see M plus and M minus species rather than here M plus H plus or M minus H minus in EASY. And I haven't mentioned it yet, but just to remind you all that mass spectrometry is actually a mass to charge ratio, not just a mass on the mass spectrum. And this is because you can actually have multiple charge species. So if you start to see, for instance, your isotope pattern coming at 0.5 mass units, this is already a warning that your Z or your charge is actually 2, and that the mass is actually double what you're seeing in the mass spectrum. So the role of a mass spectral library is actually to help you to put a structure to the spectrum that you give the library, and preferably with a score so that you know how well this actually matches. So what I'd like to do is just show you one example, or the examples of the scores that I actually like to use a lot from the NIST library. You've also seen already a lot of my screenshots have been from the NIST library. What's very important to you when you use a library is that you know what the scoring system is and what this scoring is telling you. So I'll just run through what the NIST scores do. What you can see here on the first two columns that are circled in red is we've got what's called a match and a reverse match. So these actually compare the query or your unknown spectrum with the library entry. So the match gives you a direct match factor between your unknown and the library. The reverse match actually ignores peaks that are in the unknown spectrum that are absent in the library spectrum. So this will be a way of ignoring maybe some of the noise in your spectrum. NIST also lists their criteria for the score. So a score of 999 is a perfect match. You can see this top entry here. I just searched the library spectrum against itself. Above 900 is an excellent match. 800 to 900 is good match. 700 to 800 fair. Below 600 is very poor. So if you're getting a score below 600 in your NIST library, you should be thinking about whether this is actually a good match at all or not. A match of 0 means you've got absolutely no peaks in common. What we also have in the NIST scoring is what's called this probability, and this is the percent likelihood that this spectrum is the correct answer. What you can see here in the probability is that we've actually got 5 entries that are 98.3. These all belong to atrazine. What NIST has also got is it's got the main spectrum, which is in main library. This is the one labeled with M. And you can see all the ones with an R are actually replicate spectrum. So this is behind the library. It helps the library to see what the uncertainty is in the mass spectrum. You can see the match and the reverse matches change, but it knows it's the same substance and that the identification is highly probable in this case. 60 to 70% are actually quite common cutoffs. What you can see here, 98.3% tells us that this library is very sure that atrazine is right because there is nothing that's very similar to it in the library. The but that belongs to this is that compounds with very similar spectra in the databases can have very low probability values. And I'll give you a little example here of this is a dimethyl aniline. What you can see here is that basically the spectral match was a 2,6 isomer, but we've also got the 2,4, the 2,5, the 2,3, a 3,5, and these all have very similar spectra. You can see here their match and reverse match values are actually very similar. The probabilities are also quite low and very similar because the library cannot, in this case, tell you with great confidence which of these isomers it is. So you would be quite confident that you've got a dimethyl aniline, but you would not be extremely confident exactly which one it is based on these results. So to get back to one of the main topics of this webinar is to give you a little overview of the different libraries that are out there. And again, we've only got 40 minutes. I will not be able to give you a completely comprehensive overview. What I would like to do with this webinar is to actually give you a whole lot of information of where to look for the resources that may best suit you. So I've tried to pick out a good distribution of resources, and I hope this will give you a good pointer to where to look. So what you can see here for GCMS or EIMS libraries is that actually the number of structures, which are shown here in orange, and the spectra, shown here in blue, are usually reasonably similar for all these different libraries. GMD is a little bit different, the Gold Metabolome database, because they have a lot of unknown spectra in the library where they don't necessarily have a structure. But in general, they're around about the same order of magnitude. So we have some really large commercial collections. This is like what I was mentioning earlier. EIMS has actually been very well established for many decades now. And this has given us plenty of time to grow large libraries. NIST 14, this is the library I've mentioned a lot so far. This has over 270,000 spectra of 242,000 compounds. What NIST also has is these retention index values that will help you confirm also based on chromatographic information. So they have around 380,000 retention index values of 82,000 compounds in their library. And they also have the associated software to help you match retention indices with what you've actually measured. There is also a much larger collection, the Wiley 10th. I've never had the pleasure of owning this collection. This has about 700,000 spectra of around 638,000 compounds. You can also purchase these collections combined, and together that will give you not quite 1 million spectra, but you're getting close. Both of these are actually compatible with most instrument manufacturers, and this is usually the way that most people use them, is basically through their vendor software. We also have the GOLM metabolome database, and this is actually offered or hosted by the Max Planck Institute in Germany. What I really like about GOLM is the fact that they've also referenced unknown substances that they're frequently observing in their samples. So their library basically will have mass spectra and retention time index of both pure reference substances, as you see here, the ones with the information, but also of their unknowns. This is what they call MSTs, or mass spectral tags. We also have the FEENlib. This is hosted by Oliver Feen's group in the US. And their collections are around 1,000 identified metabolites that they screen. You can also purchase these for GC quadrupole or GC TOF spectrometers, or you can query them in Binbase. There are a couple more libraries. This is why I've got the star on this slide. So basically HMDB and MassBank, I will cover these later under LCMS because they actually have both. There are also plenty of other collections available, which again I will not cover today just for time reasons. So just to recap here on the GCMS libraries, again, one of the features here is that we have a large or a very similar amount of structures to Spectra. What you can see if we move on to MSMS libraries is that this picture changes very quickly. So a feature of MSMS, because they're quite young and because the technique is actually less reproducible, there is a huge discrepancy in the number of structures that are in the databases and the number of spectra that belong to them. What you can also see is that we have a whole lot more resources than GCMS, because no one or two resources have actually established themselves as the best or the one that is most used yet. What you can also see now is that I have some stars on some of the databases. So MONA, MassBank and HMDB are mixed collections. And what I have tried to do on this graph is to represent the LC MSMS spectra. So MONA actually has, well, all of them actually have a lot more spectra. I've tried to do the fairest comparison possible. Please do not take these numbers as complete gospel. Some of these libraries are very dynamic and growing by the day. Also, it is very hard to break down the number of structures in a comparable way between these databases. For a lot of them, you can access the structure list and actually properly compare the substances. For some of them, you can't. So take these numbers with a grain of salt. They are indicative. I've done my best possible to compile them in a fair way, but these could change very rapidly. So you might ask, looking at all of these different resources, what makes a good library? Is it actually the quality of the library? Is it the quantity of the library? Is it their coverage? Is it the structures they have in it? Is it the relevance of the library? Is it the services that the library offers? And the reality is, this really depends on your question. So I personally also use several of these different libraries, and depending on the question I have, I will start with a different library. So what I would like to do is, in the next few screenshots, just give you an overview of my personal opinion of some of these libraries, a quick summary of their main features, what I see as good points, some neutral points, maybe some of the disadvantages of the different libraries. I've tried to also give you some hyperlinks so that you can start looking at these libraries and find out which of these actually best suits your purpose. Starting off with Metlin, I've got a very strange ordering. It is in no priority whatsoever. Metlin is one of the largest collections out there. It has a very consistent format, so it's basically an adjuvant QTOF, easy plus and minus at 0, 10, 20 and 40 electron volts. This makes it a really nice collection, especially if you have an adjuvant machine, because you are getting exactly the spectra that you will see in your own machine. They have around 72,000 spectra of around 14,000 metabolites. They are open. You can have a web interface, and if you use XCMS Online and other software, you can actually access this very well. If you have an adjuvant machine, you can also get the library, the Metlin library with it. But it's semi-open in some ways. It's not downloadable. What I do like about Metlin is you can do some nice exploratory work with their spectra, so you can have an interactive flyover and get some fragmentation information for the different mass spectral fragments. GNPS is one of the newer libraries out there. This is the Global Natural Product Social Molecular Networking. What you can see here from this very busy screenshot is that they actually have a large number of individual collections, and you can actually download these individually, depending on which ones you'd like. What they also have is what's called a user library that you can also download all of their spectra, and these are user contributions. So GNPS is a fully open, downloadable and individual collection, so you can choose basically which you want to download. The advantage of GNPS is that you can actually contribute and upload your own data. They have MS-MS of adducts and also unidentified structures. You have around 8,800 MS-MS spectra. This is constantly growing, especially with the user contributions. GNPS also comes with a lot more features with repository search and live update functions. You can also do some nice data exploration work, and I've just given a couple of links here which are some personal things that I've searched on GNPS. One of the disadvantages is that they have very few negative mode spectra, so the vast majority of the spectra are actually positive mode. They have quite limited and then sometimes incorrect information about the compounds and spectra, which makes it quite difficult to use some of their information. And they do not do very much spectral cleanup. So they have what's called a gold standard, but compared with some of the other resources that I'm going to mention today, their gold is not comparable with what other libraries would call gold. However, it's a really useful service, and it's also been published in Nature Biotech earlier this year. As many of you have probably guessed by now, I use the NIST 14 library quite a bit, and this is just a screenshot from their MS-MS collection. What you can see is that NIST have basically recorded a lot of different spectral types for their substances. This means they have really a lot of spectra in their library, and you can also start to see the variation that's happening with the difference. So they've got here triple quad, you've got QTOF, you've also got orbitrap spectra, even ion trap spectra. So this is really a nice data set to see what kind of spectra you could expect from different instruments. It's a very large collection. They've almost got as many spectra as their MS collection, but many fewer substances. So it's only about 9,000 substances. Only in inverted commas, because this is actually one of the largest substance collections. It's very well curated. They've actually documented this in quite a nice paper. They also, what they've done is they have MS-MS of many adducts as well. They also have, like I've mentioned, spectra from multiple instruments. This makes it actually a nice collection. Users can integrate your own library very easily into the NIST software if you have it in the NIST format, and I actually do this, for instance, for the mass bank spectra, as you can see here. And this is also integrated into most vendor software and workflows. A plus or a minus, some people consider this a plus. I, for instance, would do this. Some do not like the fact that it's offline functional. So a lot of the other mass spectra I mentioned today, or libraries I mentioned today, are online, so they're web interfaces. This one is offline. You need it on your desktop, but this means it's a very quick search. NIST is a commercial license. This is one of the downsides, but it's a great investment in money. It does have a lack of external identifiers if you're trying to connect it to some of your compound databases, and because it's a commercial license, this can be quite difficult to integrate into open workflows because they have protected their data. But there are also, there's a nice article also from Steve Stein in 2012 about mass spec libraries as well. MZ Cloud is another very new collection. It has by far the most number of spectra of any of the libraries now. This is also online, and you can see they have a really comprehensive interface. What I like about MZ Cloud, they have several layers of information. They've actually linked out these different layers. So if you want to refer to all the spectra of a compound, you can cite just a compound link. You can cite certain trees, or you can actually cite an individual spectrum. So this actually makes referencing the spectra really easy. Like I said, they have by far the highest number of spectra, so they hit 1.5 million just as I was preparing this webinar. My first copy of this webinar had 1.49 million, and their number of compounds is growing by the day. So they're at 5,700 compounds, which is quite a bit lower than NIST, but growing constantly. This is very well curated. They actually have the raw and the process data available for their records, and they will do the curation for you. They have spectral trees and also MS-MS of many adducts. This is all high-resolution data, orbitrap instruments, and the spectra are very well annotated. So they have formulas, structures, and also quantum chemical models annotated to their spectrum. Again, this is growing and updated constantly. Users can contribute. If you can get your raw data to MZ Cloud, they will basically do all of the curation for you. Again, this is a semi-open resource. It's not downloadable or batchable at this stage, but it is on a web interface. And I hope I get this information correct. This is my current understanding, is that there is a commercial license available for extended functionality. And at this stage, this is only limited to Thermo users. But if you do have this access like Metlin, this is a great resource for you. And this makes it unfortunately difficult to integrate into open workflows. The MS4ID is a small MS collection from Wiley. They actually have several others, but this is perhaps the most relevant. This is a high-resolution curated collection of forensic toxicology collection. So this is drugs, pharmaceuticals, and pesticides. You can purchase this, but it's a relatively small collection. If these are exactly the substances you're looking for, this is probably a great idea to go for. I don't actually have access to this data either. The Wishart Lab has actually a great number of different web servers. I've just selected a few of them. So HMDB is probably the one most likely familiar to this audience, the Human Metabolome Database. They also have DrugBank, FoodDB, and T3DB, and several others. What's nice about their collection is they actually have all of their information on cards. So if you want to find out a lot of information about a substance, this is mainly what these resources are designed for, and the Spectral information is an added bonus. So their main function was not necessarily a Spectral library, but they offer some nice data. What you can see here for caffeine is that they have in this card, they have basically all of the spectra listed. You can see GCMS spectra, you can see LCMS spectra, and they also have predicted MSMS spectra. So they have MS or MSMS data measured on around 9,500 substances. These are also fully downloadable collections, so you can actually access all the data. The spectra come from multiple instruments, low and high resolution. And again, as I mentioned, these include predicted spectra. This is actually predicted with CFMID, which I'll mention right to the end of this talk. And these are cross-linked to other resources as well. So you can see here there's a splash key that I'll mention later, and also they're actually linking all their spectra back to Mona, which is another spectral database that I've not yet mentioned. Again, a plus and a minus with this collection is that they have mixed collision energies and instrument types. This can make it a little difficult because it's a reasonably small collection. And what I find is the only minus is that their collections are quite fragmented. So not all of their compounds are in all of their resources, so it's difficult to see what is where. But this is where they have addressed that with actually cross-linking their resources very well. WiseMass is a database that actually just came out very recently, and you read the paper a couple of weeks ago. This is actually a shot of how they acquired their data that I took from the paper. So they have basically had a large reference data collection about, they started with 3,500 parent metabolites. They could get mass spectra for 3,300 of them. They measured these all in mixes, which is what you can see here, the chromatogram. And they've done a consistent MSE acquisition and spectral annotation on their library. So if you're into plant metabolites, this is a really nice collection for you. This is only available for academic use on request only, and I have not yet managed to put my request in. So I can't say terribly much more. Making a start on MassBank, some of you may have noticed I haven't mentioned this yet already. MassBank actually started in Japan in about 2006, and you can see the web address here, and was published in 2010. This was one of the breakthrough MSMS databases probably. Currently we have around 54,000 spectra of around 4,100 substances. This is a public repository of user contributions, and the original model was actually a distributed model where all the users could actually contribute also a server. This has changed now. We only have two main servers, the MassBank JP and EU. We have downloadable open data associated with MassBank so that you can also access the vast majority of the data. Some of them have different license conditions. And this is also a mixed database. So this has spectra from multiple instruments, electron impact, easy, low, high resolution. One of the downside of MassBank, because it was a whole lot of user contributions, is there's a very mixed quality of the spectra. There are some very high quality spectra, but there are also some quite low quality spectra. And the services are out of date. It was founded so long ago. The nice thing about mass bank is that it was really the start of exchanging spectra around the world. And what you can see here is a list of all of the different consortium members. There's a couple missing. Of course, there's a lot of groups in Japan because this is where it all started, but it's gradually moving throughout the world. What you can see here marked on the picture still is the different mass bank servers. These were the ones that are originally part of the distributed system, which no longer is quite as active as it was. We actually founded a European server in late 2012. This is actually hosted at the UFZ in Leipzig in Germany. And this was actually hosted together with the Norman network of environmental monitoring laboratories. And we took part in this to try and enhance the number of environmental substances in mass spectral libraries because we had the impression there were far too many metabolite spectra and not enough of our own spectra in libraries. So since we started those efforts, we've actually introduced about 16,000 mass spectra, mainly of environmental contaminants, of around 1,200 substances. One thing that Mass Bank EU does have, so the green I've shown our contributions, these are also available on Mass Bank JP. In the red, actually some tentative unknown or literature spectra, which we've started playing around with to extend the capabilities of Mass Bank, but these are not actually available on Mass Bank JP. So that's the only main difference between our two servers. The latest Mass Bank that was released recently is the Mass Bank of North America. And in contrast to Mass Bank JP and EU, Mass Bank of North America actually has a different data set behind it. It has all of Mass Bank plus a whole lot more. So you can see here is the screenshot. This is also hosted by Oliver Fien in the States. Mass Bank is basically now the largest collection of fully downloadable open Mass Bank data that exists. And you can see here also in the screenshot it has a whole lot of different collections that you can download, or you can also just download everything. So they have around 204,000 spectra. Around 139,000 of these are actually in silico spectra, and 64,000 are experimental spectra. And 44,000 of these are the LC-MS-MS spectra. And again, this just shows you a little bit of the difficulty it is in comparing all of these resources, because breaking down the numbers in a consistent way is quite difficult. In total, they have spectra from around 72,000 substances, but again, a lot of these were in silico. And around 14,000 of these are experimental. These are what's called unique first block incher keys, so this is completely eliminating the stereochemistry because these different resources deal with stereochemistry in different ways. As I've mentioned, these are fully downloadable collections. We have spectra from multiple instruments, low-high resolution, predictive spectra. They have great cross-linking to other resources, and Mona is actually really great to incorporate into your workflows. The developers are really open to feature suggestions, and this is again a plus and a minus. Although Mona is in development, it's not static or fully functional, but you have the ability to actually change the way that Mona is working because they're developing it right now. One of the downsides is their format, which is great for informaticians, but let's just say less ideal for users. It's very hard to read. And their automatic curation annotations are still under development, but they're doing a great job. And Satyan was actually helping me a lot this week, trying to get the numbers up to date. So taking a step back at what different resources do people use, and because I've got the environmental background, this is an example from an environmental study. We actually had a collaborative trial in 2013, 2014, where we had a whole lot of European labs participating, again under this umbrella of the Norman network. And if you just have a look at this table of compiled results and resources of what each of these different laboratories used, you can see that everyone is using different resources. So some people just identify based on compound databases, even without spectra. Some people use the main libraries. A lot of people used vendor-specific libraries, and you'll probably notice I haven't actually mentioned terribly many of the vendor libraries today. I don't have a very good overview of these. This table serves as part, but these are obviously what people use in connection with their instruments, so this decision is made by your instrument and not necessarily by yourself. What many people also do is they use their own in-house lists of libraries. So this obviously makes comparability in science somewhat challenging. What we also did when we were compiling the results from this collaborative trial is asked, do we actually need all of these different resources? And the answer was surprisingly at this stage, yes, we really do. So what you can see here is a Venn diagram of 4 of the main resources. So what I've done is we've got NIST here, we've got Metlin, we've got MZ Cloud. The numbers for MZ Cloud are way out of date. This was a 2015 figure. So their number of 733 is probably way higher now. What we also did was compile all the open data into one. And what you see here is the number of unique substances, excluding the stereochemistry again, to each collection is actually very large. So NISTA around 3,500 unique, Metlin around 6,000, MZ Cloud at this stage 700, now probably a lot more, and the open data 4,000. So this really gets back to the point you will have to choose your resources according to what substances you're looking for, and even consider using all of them. One important way to address this is to actually start to improve the library coverage by sharing your data, and this is what we've tried to do in RMS Bank. There are also several other different softwares around there that can help you to convert your raw data into Spectra for a Spectral library. What RMS Bank does, it actually collects your LC-MS-MS raw data and your compound list, as preferably as a SMILES or a name. We'll then perform automatic MS and MS-MS detection, recalibration, cleanup, remove some interfering peaks, and then actually use web services to perform all of the annotation for you so that you don't have to search out all the individual identifiers yourself, but we can do this work based on the SMILES for you. We'll also annotate your spectra with the experimental details and prepare these already in a format that will allow us to upload this to MassBank. This was basically how we managed to, in such a short time, get so many spectra into MassBank EU. What we've also been working on with several representatives from the different resources I've mentioned today is to actually improve the communication between the libraries so that you will hopefully in the future not have to go to all of the libraries, but you can actually query them all at the same time. We've done this by what's called the splash key. So this splash is actually basically a little mass spectral summary in a little line of text. Here you've got a summary of the top 10 peaks, a little histogram, and here is the hash of the full spectrum, which will actually tell you if you've got a unique resource. What we can do now is actually build URLs to access individual spectra based on this code, but you can also do a mass spectral search, for example in Google or any other web query, using exactly this code. So what you can see here is, for instance, if we type the exactly this splash code into Google, you can see this record turns up in all of the resources from David Wishart. So we've got the Human Metabolome Database, FoodDB and Drug Bank, all containing exactly the same spectrum. If we try another one, codeine, you can see, for instance, this one is in Drug Bank and it's also in MassBank. Taking another example, you can see here this was a record we actually uploaded to MassBank, and here is its splash record in MassBank. This is exactly the same spectrum that was actually uploaded to Drug Bank and also into GNPS. They've said they've got it from MassBank. It's exactly the same spectra, and we contributed our raw data actually to MZ Cloud. What you can see here is that their splash code is slightly different because they have done different processing on the spectrum. So you can see here the splash really helps you to find exactly the same mass spectra but also similar spectra as well. Getting towards the end, but I'd just like to cover a few more facts for you, just to let you think about how certain you are with your identification, and especially talking about probable structure by spectral match. So if you're looking at non-targeted data, this is an example from the environmental world, but it's very similar in metabolomics. If you're doing target screening, you'll have, for instance, a reference stand in-house, and you will basically, if your data matches, you'll be starting at a reference standard confirmed structure. But if you're doing what we call environmental world suspect screening or non-target screening, where you're starting with unknowns, you will need to try and prove this identification. And you can see here I've highlighted in orange what's called this probable structure by library or diagnostic evidence. So here the mass spectral library could help you to get to this probable structure, but you need to be sure what the library is telling you. And just to show an example to interpret this with care, this is an example actually from our own work, where we had this tri-isobutyl phosphate, and we had a non-target in our sample and a standard measured with absolutely identical conditions, and we have one of the best similarity values you could ever hope for, 0.9998. This is actually calculated with Ogg-Mass-Becker and R. And even if we scale the similarity, scale the intensity down a bit, we still get a very high value. But you can see that all your information is basically in one peak. And indeed, if we go to the NIST library and look at a library spectrum acquired on a totally different setup, this is now a different compound. It's the tri-butyl. And what you can see is that we get a very similar similarity value again. So you will basically not be able to tell the difference between these two isomers with that spectrum. So again, just to think very carefully. Be very cautious with single peak spectra or with spectra that only have 1 or 2 peaks, because these similarity values will not help distinguish. That gets back to the probability value that NIST also gives with their spectra. What to do if your spectrum isn't in the library? Should you panic? No, of course not. Basically, there's a whole lot of different in silico fragmenters out there that can help you. I'm showing these just very briefly in alphabetical order. We've got CFMRD, which I mentioned earlier. This is actually what they use to calculate the predicted spectra in HMDB. We've also got CSI Finger ID, one of the newest ones out there. Magma, Magma Plus, MetFrag, and MS Finder. There's also several more resources. I've only mentioned these ones because they were actually the ones that participated in the CASMI contest this year. And the CASMI contest is basically a way that we have of allowing the developers of some of these softwares, and actually anyone who wants to participate, to compare the performance of their methods on a standard data set. So if you would like to find out more about how the different methods actually stack up against each other and for which substances, then you're welcome to check out the CASMI contest. And I've already given my feedback to the EMN committee that I think it would be really great to have another webinar on in silico fragmenters, but there was absolutely no way that I could fit this in today, because as you can see, we've filled 40 minutes quite well just with mass spectral libraries. So with that, I would like to just wrap up very briefly. Mass spectral libraries for small molecules. I hope that I've managed to show you today there are very many different mass spectral resources out there, and I hope you find this webinar useful to find the ones best suited to your actual purpose. Always take care when interpreting your results. Is the answer really clear? And please consider contributing your spectra to open repositories. What we've actually seen in this year's CASMI contest is that the amount of training data out there has really improved the different methods, and the more that is out there, the more we're actually going to improve all of the other software solutions for metabolomics as well. So the more the merrier, but high quality annotation is really important. So don't just dump your spectra. If you can annotate these in a really high quality way, it's really worth the time investment, because this really helps us down the line. With that, I would like to thank my department here at ERWG, and especially we've had a few big rounds of creating reference standards for MassBank, so this, we tend to do this at Christmas time, because that's when the instruments are free. I would like to thank the Norma Network, who sponsored a lot of this work, along with 2 of my partners at IPB and UFZ. Solutions Project, who's also funded some of this work, and a great thanks to the mass spectrometry community. It's actually been a great pleasure to work with a lot of them and get to know them over the last few years. And again, a reminder, you can pull my slides from my website if you'd like to use all the hyperlinks. And then finally, thanks to all of you for listening, and I'm happy to take any questions.
Thank you very much, Emma, for an excellent and insightful presentation on mass spectral databases. And also, I want to point out that keep an eye on the EMN resource, the Metabolomic Society website, or the forum for our next webinar, which we intend to organize in November. We are currently working on organizing a speaker for that, so the date and time are to be confirmed. So, coming back to the question session, we have quite a couple of questions. So let's start with some GCMS related ones. For example, here, in a typical GCMS run, say plasma samples, what percentage of compounds is expected to be derivatized and what remains underivatized?
Oh, that would really depend on your compounds and your analysis. So
can you give an example for what you're expecting?
I was just about to say, so from my experience, we actually run environmental and we don't derivatize at all.
Okay.
So we would have nothing derivatized, but the reason I mentioned it is that metabolomics, I know it is very common. So I do actually not deal with derivatized spectra very much at all. The only very little experience I have is actually within the Solutions project, we're playing around with derivatizing LC-MS-MS spectra, but I'm afraid that's one I can't answer.
Yeah. No, that's all right. I think there's plenty of literature out there that should help out. So another one, GCMS related, with high resolution GCMS and Orbitrap GCMS upcoming, there's still no publicly available high resolution EI libraries yet. So for unknown compound identification, is HR GCMS too optimistic at the moment?
So I know a lot of people that are actually using these in combination, because you can still use your EIMS library to get the low resolution information, and without having actually seen GC Orbitype spectra, which I would love to see. I would imagine the basic spectra is very similar unless you happen to have had high resolution peaks, or peaks that were in the low resolution were summarized as one and they would actually split out in the high resolution. And this actually brings us back to the fact that these accurate mass libraries are still growing, and I can imagine we would have to start getting EIMS libraries happening. The reality is that none of the collections have actually started having a significant amount of spectra yet. Again, this gets back to my point. Consider contributing your spectra to help get it started.
Yep.
But I imagine a lot of these vendors are actually also taking care of that. So the first thing you're going to get is actually a vendor library.
So here's a question that relates to that. What is the easiest workflow to clean up your own spectra and get them into a database, local or open?
What is the easiest workflow? This depends. So we've developed RMS Bank. This works extremely well for the Orbitrap spectra that we developed it for. And if you have the acquisition and everything correct, I think WiseMass used a very similar. What you can now do is measure in mixes and start off with a list. It takes you a little while to get to know the software, but if you're comfortable in R, you can actually have a couple of goes, and then once you know it, it will actually effectively run in the background. So you have quite a high dig-in, so you have to learn quite a lot at the beginning. If you learn that, then you can manage to do hundreds of spectra, or even thousands. If you really don't want to bother with all of that, then MZ Cloud is the way to go, because if you've got the right data that they would like to have, they are willing to take your raw data and do all the processing for you. So again, this is really, it depends on what you as a user want to do, and on your end purpose. So we've actually found the NIST people actually helped us to get our mass bank spectra into NIST. They themselves do not want to accept these spectra because they're a standards institute. So instead of adding our spectra to their database, they've enabled us to get our spectra into their format and use it within the database, but they're measuring their own.
Okay.
Again, it really depends on what suits the different users.
Yes.
Mona also, and GMPS, they also all have different forms of uploads. So the thing I personally don't like about GMPS is they don't do enough checks and they don't do enough curation when you're adding it. So it's very easy to add your spectra, but it's very, the onus is on you to do all the information, and there's actually better ways to collect information now.
So here's a question that relates to that, because you mentioned a lot of like high quality and low quality spectra. So what would you say is a high quality spectra, and what would you say is a low quality spectra?
Well, again, this depends on the situation, but you can tell, for instance, in MassBank, you can tell just by looking at some of the Orbitrap spectra that they've really just copied exactly what comes out of Excalibur. They've got all the noise in there. You can see little trees. You can see some peaks coming above the mass that you've actually acquired the spectrum at, so you've basically got electronic and instrument noise in there. And the same actually applies to a lot of the TOF spectra that have a lot of background as well. With the high quality spectra, we, for instance, we do formula annotation so that we know that the peaks we're actually reporting in our database make sense according to their sub-formula, because we know what we start with. We've also done a lot of checks when we're curating, so we make sure that our smiles matches the mass that we've extracted, that matches the identifiers that we've got in our mass bank record. And again, this is the way that you actually address it with the curation. So for instance, some of the GNPS spectra, the substance behind it is the salt, which is not what you see in the mass spectrum. So if you calculate the mass of the compound, it doesn't match the mass of your mass spectra.
Yes.
Little things like that. So there's a lot of different ways you can see whether it's high quality or low quality. And again, some of them, low quality curation, you can actually have very nice mass spectra behind it.
Sorry, you can have a nice?
You can have low quality annotation with a nice mass spectrum. You can also have a nice mass spectrum with low quality annotation.
Yes.
Yeah, it's a really big mix.
So when you say high quality annotation, you mean that all the fragment peaks are assigned with
also the fragment peaks, but also the chemical information annotation and the chromatographic annotation. Okay. So for instance, you've got a retention time reported, but you've also got the chromatography reported with it.
Yes.
And that you've got the chemical information matches the chemical information that is actually off the record. Things like that. So making sure that all the information matches, basically.
Yes. So this question relates to that. Are there LCMS-specific databases where RT information is recorded?
Yes. So, for instance, in MassBank, not all of the records have retention information, but the vast majority, in fact, all of the ones processed with our MassBank do have retention time information, not retention index, sorry. So they have retention times, and they also have the reported chromatography. And we've actually uploaded most of this to PredRet so that you can see for the different records what the retention time looks like for the overlapping substances. So there's about 4 or 5 different contributors that have added Spectra via our MassBank, and these will all have retention time information, and some of the other ones as well.
Okay.
The caveat with that is that you have to be very careful. All of ours are in minutes, and it's actually annotated with minutes. Some of them are just a retention time, and it's not actually clearly annotated with as seconds or minutes. So if you're doing a bulk summarizing of MassBank, you have to be very careful with the units.
Yes, and I think also to add myself to that, I mean the gradient used and the column, etc., are also obviously important for any retention time. So
yeah, so in our MassBank we actually annotate all of that unless the user has not filled out those settings in their setting file. So for all of the records that I've seen, we've got a retention time and the chromatography in the column that goes with it.
yeah. So here's another question. I think that's more, it's both for GCMS and LCMS the case. So if you get a good database hit, is there a good way to satisfy yourself that some compound not in the library wouldn't fit just as well?
The best way to do that is to put your thinking caps on and have a look at it. And I mean, just sitting back and having a look, so I showed already the example with this dimethyl-aniline. It's quite clear to anyone with a reasonable chemical knowledge that it could be the different isomers would have very similar spectra. There are some cases where the isomers actually have very distinct spectra. This will be the same with alkenes. NIST has a very good alkane or alkene database, and it can actually tell you with reasonable confidence which one does match. But if you would think about it a bit more, you could see there are branching possibilities that may or may not influence.
Yes.
So again, this is where actually the libraries can help you by also printing structures next to the fragment so that you can see if that fragment is really distinctive for that molecule, or whether, for example, if the fragment is just a benzene ring, it could be any molecule.
Yes.
So again, it's just basically a visual reality check at the end, and this is much more difficult if you're doing high throughput data and actually working on decent values to communicate to the user your confidence in high throughput is actually going to be really important in the next few years in metabolomics.
If I may, I can add that one way to satisfy yourself as well is to take the structure, search in ChemSpider and PubChem compound libraries, which are huge. So they contain a lot of compounds, and you
Absolutely,
can
yeah.
similarity basis, for example, 20 motor similarity, and pick out all the higher than 95% similar compounds, and have a look to see are there a lot of isomers, are these isomers, could this be present in your sample as well, and then following that, you could argue that you have a hit, you have a good hit, but you're still, not completely there, or you have a very unique hit and you're quite happy that it's that compound.
Yep. So what we've actually tried to do within MedFrag is we've actually connected up the MONA database with MedFrag. So what you can do now is do your retrieval with KEGG, PubChem, or ChemSpider, or some of the other repositories. And what MedFrag can now do is calculate based on the INCHI keys individual compound match to the spectrum if it happens to be in MONA. And it also does this MET fusion score, which looks at the spectral similarity and the compound similarity. And if you actually plot these up for all the candidates, you can see if you've got one spectral library hit, but several that have a very high MET fusion score that are not exactly the same but look similar. Or you can see very quickly that there's one compound that matches the spectrum and it's got a very high MET fusion score, and all of the other scores drop off very quickly. And this is another way to convince yourself, again with the power of a bigger compound database without necessarily spectra, to see if you've got a very unique match or if actually everything with that formula is very similar and you've got a very low chance of telling apart.
Yes. So, view of the time, 2 more questions. So, is there information in MassBank or the more general libraries about which organisms the compounds were identified? So, in other words, where to go? I mean, say you have a plant extract, where to go first, or say you have a environmental sample, where to go first?
Yeah, so
Is there any
for mass bank, for mass bank there is a tagged field which is just gives you a little bit of an indication of whether it's a natural compound or a non-natural compound, and for all of ours we've saved NA because we can't tell if it's natural or unnatural, but we've saved that it's an environmental standard, for instance. There are other libraries like RiseMass that was specifically just developed on plant metabolites, so it only covers this this group. So again, this depends a lot on the resource. For mass bank, they've actually got what's called biomass bank behind it, which is a separate collection, and this is only of biological unknowns, and these are also tagged with the organisms. Sometimes the way to actually get to some of that information is to use, again, a bigger compound database or some of these more specific collections, and use those collections to get you to the spectra for what you're interested in. So for example, HMDB, it's the human metabolome database, and where they have spectra, they've linked it. So this is maybe the way you could start from the organism and get to the spectra, rather than starting from the spectrum and then get to the organism, if you see what I mean.
Yes.
Again, there's just a huge diversity of resources out there to tailor to these different questions.
So the last question is related to the splash keys that you showed on one slide. So how to create such a splash key?
So if I can go back to my slide very quickly. What you can see here right at the bottom left is there's this splash.fiendlab.ucdavis.edu. This basically has everything you need to know about the splash. So you can basically use some web services to create it. We've got it programmed in several different languages now. And most of the repositories or the Spectral libraries that actually participated in it have actually splash keys now for their mass spectra. So you can find reference splashes in quite a few places, or go to that website and find out how to do this by yourself. I'm not sure if I did mention it, but what you can actually do is chop that code also into little pieces and do very rough similarity searches as well. So if you take away the hash at the end, you can just search for a splash 10 002 09 0000 whatever, and then you can actually get to very general similar spectra. I find it really interesting.
Okay, that sounds really interesting and something that I personally would like to try as well at some point. So with that, I'm afraid we're out of time for further questions. So just to say that there were a couple of questions on spectral similarities, but this might be a very good topic for another webinar, perhaps in relation also to in silico spectra, because there was also some questions on how well can we compare in silico spectra with experimental spectra. So yeah, and to finalize, so this webinar, but especially also the other 9 are available from the Metabolomic Society website. If you go to the tab Resources, you'll find EMN webinars, and in there you'll find links to the 2015 ones and to the 2016 ones. So with that, I would like to thank all of you for your attention, and we will close the webinar. So thank you, Emma, again. And
thank you all for listening.
Thank you all for listening indeed and asking very interesting questions that we could discuss. Thanks.
Thank you.